tonight, for our speaker, we're really excited to have with us Rick Hill. Rick Hill has been a member, a Tucson Amateur Astronomy Association member since 1979. I figured up today, Rick, and if my math is somewhat accurate, I think that's like 42 years. So we're delighted to have had, all this time with you over all of these years and all your contributions. And we're so glad that that you can present for us tonight. So I think that Rick retired recently from the Lunar and Planetary lab at the University of Arizona. I don't know how recently you retired. So Rick, when was that?
2015.
Oh, well, further back than I thought. Okay, well, good. So you have probably mastered retirement now and figured out how many astronomy activities you can accomplish during that period of time.
Astronomy and paleontology.
Okay, wonderful. Well, I will let Rick start with his presentation if he's ready to screen share. And you might want to start with the title since I didn't mention that.
Okay. Okay, so this is solar cycle 25 we're going to talk about. We'll also be talking about energetic solar phenomena associated with solar cycles. And then lastly, we'll talk about Association of Lunar and Planetary Observers, how they observe the sun and what their contribution is to watching the solar cycle. So what is a solar cycle? Well, the bottom part of this graph shows the last 100 years of cycles, actually about 130 years of cycles. And you can see, let me see if I can compress this. I've got there. You can see all these cycles, and you can see that this is the one that just ended down here on the extreme right side. And it's a small one. It's a small cycle. Whoops. It's a small cycle, smallest since about 1910. And they've been getting smaller recently. And we're not sure why. We don't know why the sun does these things. We're all on for the ride. Up above is what's called the butterfly diagram. Sunspots have a tendency early in a solar cycle to form at high latitudes, plus 30, minus 30 on the sun. And as the solar cycle goes on, they get closer and closer to the equator. So at the end of a solar cycle, you'll have old cycle spots down near the equator and new cycle spots starting to appear up at plus and minus 30. And if you plot them all according to their longitude, you get this butterfly diagram. The first solar cycle was in 1755, and that was designated by Rudolf Wolf, who lived in the 19th century. He didn't live in the 18th century, but he started with 1755 for reasons you'll see shortly. Now, the recent 4 cycles, notice that they've all been getting smaller. And they've also, for the last 3, have been double peaked, their maxima, which is unusual, not so much to have a double peak, but to have 3 of them in a row. And they've been getting smaller and smaller. The activity's been dropping lower and lower, and we don't know why. Like I say, even the solar astronomers are very much on for the ride, trying to understand all this. You can see in the spotless days on the sun, when there were no sunspots, the number of those days that we did pass through the minimum right in here. And 2019 was the minimum. NASA and CILSO, which I'll explain in a second, in Belgium, designated December 2019 as being the bottom of the period between solar cycle 24 and solar cycle 25. And 281 days of no sunspots pretty much says it. We are picking up a little bit now, so there are less days of no sunspots. And of course, at the maximum, you're going to see whole years with no sunspot, with no 0 day counts, which would please the people that count sunspots. Here's a close-up of the last cycle. You can see the double peak That's a trend line run through all the data. The yellow is the daily sunspot count, so to speak. It's R sub I, and the blue is monthly averages. Now that brings up a point that most of the solar indices are computed on a monthly basis. When I was put in charge of starting the solar section of the ALPO in 1982, I decided that the sun didn't care if it was February or January. So we take our information, our data. We don't count sunspots in the solar section. We take our data and we compile it by solar rotation. And down here is where the minimum was, December. And here's the rise. Now there are two reigning predictions right now for the rise to the next maximum. One shows a steep, sharp rise to the maximum, and the other one's a slower, lower rise. When this peak happened right here last November and December, everybody got excited and said, "Oh, look, we're on our way for a nice big sunspot maximum." And I held my tongue because this can, as you see now, is anomalous, and it very well could have been. And we've dropped right back down, and we are on track for the lower, slower rise. This is the computation done by the ALPO solar section, where it's by rotation, not by month. Still, that anomalous peak shows up, but it shows up for two rotations rather than just the sharp pointed peak. And the reason for that is the large amount of sunspots that appeared at that time were crossed over on these rotations. They were right, it was right on the border of the two rotations. Now this is current as of June 30th, and we are rising. You can see that we bottomed out here and we are rising. Take heart, there will be more sunspots. The one that's on there right now is not a naked eye sunspot. We could wish for a naked eye sunspot. It's only about half big enough to be naked eye. Here's the predictions, the forecasts for the rise to the next solar maximum. And it shows two envelopes, a magenta envelope and a blue envelope. The blue envelope is the lower probability prediction, and of course the red would be the higher probability, and the red line is what we're trending right along. This is where we are. This is June 30th, and it looks like it's going to be a low, slow rise to the next maximum. And it even further, we see that here's a plot of a lot more of these maxima. Here's the 1755 one. And you can see that this was the first, well, my arrow keeps going away. This is the first solar cycle right here. And this is where we are right now. And this is the guesstimate. I'm not even going to call that a prediction. That's a guesstimate on what our next solar cycle is going to look like. NASA put this statement out about 2 weeks ago. They predict the next solar cycle will be the lowest in 200 years. Which would be back here at the Dalton minimum. And so there'll be a lot of used solar equipment going on the market if that's true. So what is this activity that is so exciting to watch? Well, the two big energy producers on the sun are flares and CMEs, coronal mass ejections. This is what the sun looks like at solar maximum. And here's what it looks like at solar minimum. This is very easily a naked eye sunspot. Now, having said that, let me say, even when you're looking at the sun with the naked eye, be sure to use safe solar filtration. Even if its sun is setting and you're looking through smoke, that's not safe. You just use the filter that's on your telescope, hold it up to the sky. You can use eclipse glasses so long as they were produced by a planetarium or somebody like Orion or Botter. Don't use eclipse glasses that were put out in 2017, for example, by a hotel, because you don't know who made those. They may not be safe. So use safe filtration and you'll be able to see these spots. This was the largest spot of the last solar cycle, cycle 24. This is done with my Questar, my favorite solar telescope. And you can see here that it would be easily naked eye. It's a large spot, and we'll look at the numbers for it in just a second here. Here's a close-up done by Randy Shivik, and he's got a 6-inch telescope and better skies than I do. This region right here is a good flare producing region, as is this up here, and over in here too. You can see that in my image, that this is the wide shape, that it either just had a flare or is about to have a flare. We had a program in the solar section called the White Light Flare Patrol. This is back one solar cycle ago. And we would, our observers would set on a spot like this. They would make a sketch of it. And every 10 minutes, they would go out and look at these areas that are likely areas for flares. And you would know what you would see when you did see a flare is you'd see a bright point form inside there. And then 10 minutes later, there may be 2 or 3 bright points in there. Or if you see bright points, you might want to come back to the telescope every 2 minutes and watch. And you would note it, and you would see it spread along the whole area here. Or in here, you'd see a granule. These are granules right here. This is granulation. A granule would get bright, and it would spread to the next door granule, and then one next to that would get brighter, and it would fill up. It would just spread along in there. It's very exciting to see that. And the White Light Flare Patrol was a highly successful patrol. Our mentor for that was Don Neidig out at the Solar Observatory in New Mexico. And he was very impressed with what we did. We found and observed more white light flares in just 1 year of that flare patrol than were seen all throughout history up to that point. So if you know what to look for, you know where to look, and you know how to look, you're going to see these. And it's very exciting. You don't need a H-alpha filter or a calcium filter to do it. Your ordinary white light solar filtration will show it. These are the top 25 sunspot groups of the last 2 cycles. And I want to point out something. In general, to be a white light, to be a naked eye sunspot, the sunspot has to be about 900 millionths of the disk in area. Millionths is the unit of measure of area on the sun. And I don't know who started that, but that's the accepted measurement. And it's 900 millionths makes it naked eye, unless you have an eye like mine, then it's 1,000. Because my eyes aren't as good as they used to be. And I've had younger members of the solar section report 700 and 800 millionths. The sunspot that's on there right now is 500 millionths. As you can see here, these are the AR numbers. The AR is active region, and these are the active region numbers for all these sunspots. And the first digit is left off. It's either a 1 or a 2. This is the size, the areas of the sunspots here. And I want to point out, all 25 are easily naked eye sunspots. So you get about 2 or 3 naked eye sunspots per year during sunspot maximum. And these are the classes. I'm not going to go into those right now. That's a whole nother talk about how sunspots are classified and measured. Now, associated with these large sunspots are flares. And here you can see the active region numbers for these flares. And these are the strengths of these flares, X-ray strengths. This is the biggest flare ever seen in history. It was in 2003 in November. It fried the satellite that measured it. They say 28 plus because the satellite was burned out at that point. Nobody expected to see a flare that strong. This gets to something I wanted to point out in these energetic events. You can see how long that flare lasted. It wasn't terribly long, but it really peaked rapidly. all of these flares are very, very strong. And if you'll notice, they're all very early. In the last two cycles, the one closest to us now is this 9.3 in 2017. There's another 2017. Most of these really energetic flares occurred before we had smartphones, before we had navigation systems in our cars, before we had all this delicate electronics, and we don't know how these electronics are going to be affected by this. These are powerful events. Now, the top X-ray class flares are here, and these are all very, very powerful. And again, they happened quite a while ago. These are all before 2017. And there were none of the electronics that we have today. There's a lot of talk about this right now. I assume the military's probably figured out ways of hardening their equipment to protect it from this. There's a lot of articles on the web on how to harden your equipment. The safest, believe it or not, the safest, simplest way is if you have a hard drive you want to keep safe from all of this, or an old smartphone you want to keep safe from all of this, although it won't matter because the transmitting stations are going to be fried too. You can just simply wrap it in newspaper, then wrap that in aluminum foil and ground it. It puts it in a Faraday cage and it should keep it safe. But we have not experienced this yet, and we just well might, but I don't think it's going to be this solar cycle. And I don't think I'm going to have to worry about the next solar cycle after that. Now, coronal mass ejections, this is one that occurred in 2002. We haven't seen one this big in a while. We had a pretty hefty one in 2012, I'll show you. This is where charged particles are literally sloughed off the sun in a cloud. And this cloud moves very, very rapidly and can hit the Earth and create amazing aurora. And those things called Steves and all these other atmospheric phenomena that are magnetically associated. Here we see, looking down from the pole of the sun into the solar system, we see the sun in the center. The Earth is over here, straight out from the sun. And then we've got Mars up here. We've got Venus and Mercury and a couple of satellites. This shows the spiral is the solar wind. That's just the normal solar wind, energetic particles being shot out from sunspots or smaller flares. But a coronal mass ejection, as you can see this arc, is so powerful, it doesn't pay any attention to the solar wind. It plows right through it. In this case, we were missed by the CME. Here's a different one where we were hit square on, and it caused aurora. This is the one in 2012, as you can see up here, and it caused aurora, and it goes out from the sun and gets to the Earth in just a couple of days, whereas things that travel in the solar wind may take over a week to get to the Earth. So they can barely get out a geomagnetic alert when one of these pops off. Here's a big one that missed the Earth, and I think we should be thankful for that. This one was very powerful, and you can see the Earth is still in the same place, right over here. And this one plowed out through, but it was caught by the satellites. This is, let's see, the blue one is stereo B, and stereo A is up here. And this is Kepler over here that got hit by that. Not very bad though. Kepler just got lightly brushed by it. But these coronal mass ejections are very powerful events, and they occur more frequently at solar maximum. And if we have a suppressed solar maximum, we may be very grateful for that. Now, this was a sunspot group that created a flare that was a record setter too. This one was back in 1989. And when this created a flare, that flare shut down a power plant in Canada. That power plant had safety features built in for EMP, and when it felt the effects of this flare, all those switches kicked off and kicked off the power to most of Ontario. And we haven't had anything like this since. In the 1950s, we had some, but our electronics were pretty primitive back then. And this is something that is something we have to watch for and think about. And whether we get it in this solar cycle, don't know. Right now, it's not looking real likely that we're going to get this kind of power out of this solar cycle. So what about the ALPO, Association of Lunar and Planetary Observers, not the dog food, the solar section? We have a number of members all over the planet, literally all over the planet. What kind of telescope should you use? What do you got? Use what you got. That's what I've always said ever since I founded this section in 1982. You don't need to buy anything special. You can if you want. You can spend vast amounts on a solar telescope. Here's my Questar down here, and I'm showing the sun to one of the kids at Bryce Canyon. This is in my bearded days. And you can see I just got a simple Orion solar filter on there. Good telescope for showing sunspots. Up here is Theo Ramekers with an H alpha telescope showing sunspots to a kid, trying to get him to. Kids always want to rest their head on the. This is running away on me. Kids always want to rest their head on the eyepiece. I don't know why. This is Pam Shivak and Randy Shivak. This is the telescope that took that very detailed picture of the sunspot. And this is one of the observers in Belgium. This is Kim Hay. She's the assistant coordinator for the solar section. And this is me with my Celestron 5. When I don't use the Questar, I'll use the Celestron 5. Optics were made by Bob Goff. They are superb optics. They'll pry that from my cold, dead fingers. And this telescope was another one of our European observers. And down here is an ETX during the solar eclipse. Many different telescopes. You don't need a big aperture for the sun. 3 inches, 4 inches will show you quite a bit of detail. This is a 6-inch that Kim has over here. These are only 3 and 4 inches right here. Of course, an ETX is just like a Questar, 3.5 inches. You don't need a big aperture. And another thing I'd point out is one excellent material for making solar filters. You get the filter from material from Botter and then use a styrofoam board. Stuff is great. You can roll it, you can glue it, and the filter should be wrinkled a little bit because you're putting it through a lot of temperature changes from the winter time where you'll be in freezing temperatures to the summertime in Tucson where it's 110, 115. So it goes through quite a bit of thermal stress, and you want to keep it loose. This is the website for the Association of Lunar Planetary Observers. When you go there, you'll see the solar sections right there on top. And you can go straight to imaging submissions. It will show you how to submit your images so that they get put in our galleries. Here's the galleries. The solar section web page usually features the summaries of the individual rotations. Kim Hay does those. At the end of a rotation, she'll put out a summary. I use her summaries in the larger reports. They keep my focus on what she saw as interesting, and she lists all the observers for that rotation that submitted images. Right now, we're at a low ebb for observers. We only have about 2 dozen, but during solar maximum, the good maximum, we can have 50, 60 observers. This is the gallery page for the different sections of the ALPO, and there's the solar gallery. And this is what you would find when you get in there. Click on any of the images, you see a larger version of it. You'll see calcium, white light, whole disk, just small areas. Several observers are doing this. This is a a hybrid drawing. It's white light and H alpha. So he can see features of both of those. You can see how those features interact and how they affect each other. Here's a drawing. Don't hesitate to turn in a drawing. It doesn't have to be a high resolution image. The drawings have value. Like we have one fellow in Australia. He's almost daily. He lives out in the desertified part of Australia, I guess. But it seems like he's got every day clear, and he observes almost every day, except he's in his 80s. He took a fall recently, and we all gasped. But he frequently sees sunspots before they're designated by the National Oceanographic and Atmospheric Administration. And he's doing the hybrid here too. You can see the prominences, and you can see he's showing a plage around this sunspot group and prominences all around the disk. This is Monty Leventhal, does a great job. And so he's often cited in our reports as having spotted a new sunspot group before they were even officially designated. Again, this is done with my scope. On my Questar, you can see that there's that light bridge again, cutting that spot umbra in half. But again, there's the granulation. You don't need a huge telescope for all of this. You can see granulation quite clearly there. This is Monty again. He does some imaging, and this is his H alpha image of a flare. The flare is right there, but it's excited a lot of other areas in this sunspot group, and it's caused enough of a shock wave to throw off some of the material from the sunspot group. Here's another flare by one of our other observers, Guillermo Grassman, down in Argentina. And this is a beautiful picture of a flare. It would have been nice to have seen an evolutionary picture of that. We get some observers that will take a picture of this every minute or so and then put together a movie. Very, very instructive. This is Howard Skildson. He's in Florida, and you can see he's got a calcium picture colored purple and white light colored yellow. And you can see the matching features, and you can see here that there's some bright points in there that you don't see here. That's important information. Can tell you where the flare may form next, and then you can watch for it in white light. We use these kind of, and this is the sunspot that's on the sun now. This is 2 days ago. We got clouded out today. And it's got a lot of, this is the David Levy said he counted 40 spots in this sunspot group 2 days ago. So this is 20 active region 2835, and this is 2836, which has just been reduced to one small spot now. But we could well see more activity out of this one before it leaves the disk. Now this is our journal. And this is where things get published in final form. And this journal, by the way, has become an excellent journal. It used to be rather sporadic how it was published, and now it's published quarterly, and it's done on time. I have to give Ken Pashedley the credit for that. He's a professional publisher, so he values getting things out on time. And he can really get rough with you if you're a little late with your manuscript. This shows the latest article on a report on Carrington rotations. I said that we tally everything by rotation in the solar section. Here's that plot you saw earlier. This is jumping ahead on me. Plot you saw earlier, and this is the SILSO plot that we showed. And this is some more work by Howard Skildson. This is Frank Melillo down here. There's a couple of my pictures. And you can watch the evolution of the spot groups like this. When we get enough data, I'll put them together like this, where you can watch the evolution, or you can see what it's like in 3 different colors, white light, H alpha, and calcium on the same date. Same thing here. This is TAAA Ramekers. White light, H alpha, and calcium. on my white light picture, and it's not a calcium picture, it's a K line. It's a broadband on the calcium K line. And then that's being compared to Dave Teskey's combined white light H alpha drawing. Down here we have Frank Melillo's pair of images, white light and H alpha. And the same thing over here in Randy Tatum with his large refractor over there in Virginia. And there's other articles in the ALPO journal. And this is one on Daryl Nye that we just ran, our club member who passed. And he was well known to a lot of organizations and has made generous donations to them all. So I would encourage you to go to the solar section. Their link is at the bottom here. You can contact me at this email address if you have further questions, or you can visit my website up there at the top. And with that, I guess we're going to take questions.
Yes, you have one question from, I think it's 7. And the question is, how big are typical granules in millions?
In millions. I don't know the answer to that in millions. I can tell you that a granule is about the size of Arizona. And in arc seconds, they're about 1.2 to 1.6 arc seconds. That's why I can just resolve them with the Questar. I hope that answers the question.
Super. Jim, do you have any questions from Facebook?
I know Terry's watching Facebook, but I haven't seen any come across. So
Oh, that's right. Okay.
There's none, but I just submitted a question.
Okay, yes. Okay, Terry asked, Rick, can you explain the calcium, potassium filtered images? Is that a specific depth in the sun's atmosphere or something else?
Oh, yeah. Yeah, if you've seen the spectrum of the sun, it's got the black lines for the different elements. Well, the calcium filter is where they have filtered down the light that can get through so that only the light from one of the H and K lines, the K line of calcium, only the light from that K line can get through. So whatever the sun's doing in that line, it would have to be an emission or absorption, will get through, and that's what you will see. Gee, I wish I'd put a spectrum picture up here. It's the same thing as H alpha. They filter down on H alpha, but H alpha is a much thinner line, much thinner. And they filter it down to where all you're getting is the dark line coming through to through the telescope. But that dark line is really not dark. It's like a sunspot. If I were to put a sunspot in the middle of the night sky, it would be a bright star. It's only dark because it's on a very bright object, the sun. So the inside of these lines shows all that information that you saw in those pictures. But it takes a fairly expensive filter to do it, especially for H alpha. The calcium filters are expensive because they don't make as many of them. But with those pictures by Ramakers, let me back up here. Yeah, those pictures right here, that's with a celestron there, but that's with a PST and that's with a PST. So you can do some pretty good work with that little 40 millimeter aperture PST. Don't hesitate to use things like that. The only thing is you have to fiddle around with it either optically or mechanically to get the focal plane into your camera. That's been a problem for me. I haven't done it with mine yet. Any other questions?
Yes, you've got a couple more. 7 asks, the solar constant is constant seemingly because the falculi brighten during sunspot activity. Any understanding of why and what that may mean for sunspot viewing formation on other stars?
Well, we have seen sunspots on other stars, most notably the cooler stars, where they apparently are much larger. And and we've seen them. I don't think we've direct imaged them yet, but we've seen them through spectroscopy. And whether the faculae are actually brighter, you're saying during solar minimum? Was that the question, May?
Let me see, find it again. Right during sunspot activity.
Oh, okay.
Any understanding of why and what that may mean for sunspot viewing or formation?
Well, the faculae, literally, again, I can show you in a previous picture. We had a good picture of that. Okay, you can see the faculae right here. See that lighter area? That's faculae. Notice that they mimic the plage in calcium. So it's just a hot region that's hovering over the photosphere of the sun, and it outlines the plage material. Whether that has an effect on activity, I don't think it does, but I think it does let you see where the plage for this sunspot group would be. If you get a Botter K-line filter, you can see this stuff much better. And that's why I bought that filter. And as the sunspot gets away from the limb, though, it gets harder and harder to see. I think that you can see this one's very near the center of the sun, but you can see in the K-line filter, I'm still picking up a little bit of that.
Okay, Brad has a question. Individual ALPO observers vary greatly in what is recognized as a single spot. So how does the ALPO normalize all the observations together to produce a final count? The descendants of the Zurich count has a standard observer and everyone scales to them. The AAVSO method is yet more different and complicated. So how does ALPO normalize everyone together?
We don't. We don't do sunspot counts. Early on, when we first formed in 1982, I made a deal with just so they didn't feel threatened by us. I made a deal with the AVSO solar director, it was at the time, that we weren't going to do sunspot counts. We're going to deal with morphology, the shapes, the evolution, the changes in sunspots and other solar activity. And we've kept our hands off of the counting, but we do use sunspot numbers to show activity in those plots. And those numbers I get from SILSO, the World Data Center over there in Brussels. And that's recognized as sort of the clearinghouse for that. And those are the numbers we use. We don't generate our own numbers. That's a very complicated statistical analysis that they have to do for that.
Okay. Heidi has a question. She asks, how long is the sun's rotation?
27 1/3 days. Again, it depends on latitude on the sun because the sun's not a solid body, but the accepted value is 27 1/3 days.
7 says maximum to offset the dimming due to the spots.
I don't understand the question.
7, do you want to add something to your question or your comment? Oh, 7 says that was the answer to your question.
Okay, say it again. Say it again.
Okay. 7, do you just want to unmute and talk to Rick here?
Or we can take it to the breakout room later.
I think it was in reference to his earlier question. You were wondering if You were talking about at the minimum or maximum, and so he replied that it was the maximum, I think it was.
Yeah, sorry about that. Can you all hear me?
Yes, very
Yeah.
good.
Oh, sorry
very
about
good.
that. Yeah, so we had a talk at CAS a couple of, well, almost a year ago at this point. I think it was Dr. Franz who spoke about the solar constant being essentially constant, despite the dimming due to the sunspots. And one of the reasons he gave for that was that these faculae brighten during
Ah,
sunspot activity to offset the dimming, which would otherwise be seen in the data due to the
With-
actual spots themselves. So what effect does that have? I mean, this is clearly something convective in origin. So what effect would that possibly have on us seeing sunspot activity on other stars, which we're just in the infancy?
well, okay. First, very possibly that's true because you don't have faculae without sunspots. And so that's almost certainly true to some extent. Seeing it on other stars, we're just barely detecting activity on other. I think it's fascinating they can actually detect activity on other stars, but um, I don't know how they would separate the bright material from the dark material in a spectroscopic observation of another star, because they're not doing any direct imaging of that yet. I mean, they will eventually, and I hope to live to see it, but they're not doing that now. I wish I'd heard that talk. That sounds fascinating.
Well, maybe he can email you some information.
Yeah, yeah, absolutely. There's the email address. It's refreshing to know that the solar constant is constant.
We have a question from Phil who says, I've heard solar flares affect corrosion in pipelines. Is that true?
I have no idea. I've never heard of such a thing. I can't even imagine how that would work. If anything, pipelines would route the energetic activity as it got to the Earth, but just like because they'd be an antenna basically.
Donald says, sorry I came in late. Can you explain the near perfect sphericity of the sun? Why is there no equatorial bulge?
Because it rotates slowly. There are lots of stars we see that have that bulge, and but they rotate a lot quicker than the sun does. And we astronomers did try to look for that right here in Arizona. There was a solar observatory on the back of the Catalinas, and that was the sole job of that, was to look for variations in the north, south, east, west diameters of the sun. I think that was Jack Hill that did that. I can't remember.
Okay, so are there any other questions that we've not gotten to yet? If anybody has an additional question, you can unmute and state your question. Well, I think that takes care of it for this
Okay.
at this point, Rick. Rick is going to be here for our breakout room later, so for our members. And thank you so much, Rick, for the really interesting presentation and all the great information here. So,
Okay.
we want to also now have a poem from David Levy. Are you ready, David?
Yes, I am. Can you hear me okay?
Yes.
Good, thank you. First of all, I wanted to congratulate Rick on this wonderful presentation. I've known you for so many years, since 1980, 79, 80, when you first arrived here. And our friendship has just lasted over the decades. And it's so great to see you in action one more time. It was really a pleasure to see you and hear you this evening. Anyway, before I do my poem, I would like to share a photograph that you might find interesting. Um, uh, hmm. You're not seeing the photograph yet.
We just got it.
You seeing the picture?
Now we are.
Okay, great. Okay. This photograph was taken in 1980, and it was one of our winter visitors, Peter Jedicke, arranged to have this picture taken and sent to me. And as I was looking at it, I was just wondering the memories that this picture envelops. Rick, you're in the picture.
Yep.
There's young Daniel Stoll right next to you. And Peter and Diane are there. I think Diane off to the right. But Peter, not far from you, is Rolf Meyer. And we lost Rolf about 5 years ago to a very rare cancer. He passed away very suddenly after just a few months, and we really, really miss him. And this leads into the poem that I'd like to read. This poem is in honor of Rolf and in honor of you, Rick, because at the time this picture was taken, you were working at the Burrell-Schmidt telescope up at Kitt Peak Observatory on the other side of the mountain from the McMath Solar Telescope, which is in the picture. Anyway, later in your career, you went ahead and discovered more than 20 comets. And so this Hopkins poem is in honor of you and in honor of Rolf. I am like a slip of comet, scarce worth discovery, in some corner seen bridging the slender difference of two stars. But when she sights the sun, she grows and sizes and spins her skirts out, while her central star shakes its cocooning mists. And so she comes to fields of light. Millions of traveling rays pierce her. She hangs upon the flame-cased sun and sucks the light as full as Gideon's fleece. But then her tether calls her. She falls off, and as she dwindles, sheds her smock of gold amidst the sistering planets, and then goes out into the cavernous dark. So I go out, my little sweet is done. I have drawn heat from this contagious sun, to not ungentle death, no forth I went. And now, thank you very much.
Great. Thank you so much, David. You always come up with such interesting things for us. Thank you. And it was a delightful idea to bring the picture and show that. We appreciate that. So right now, we're going to express our appreciation to the Facebook people for having joined us tonight. We hope that you'll go to our website at tucsonastronomy.org and take a look around. We have lots of educational activities there and lots of things about the club. And of course, we have a nice little place that you can donate as well to the club. And if you'd like to consider becoming a member of TAAA, that's the place to do it. It's a really simple process to do. So thank you so much for joining us tonight. We hope that we see you again. We're here every first Friday of the month. And so please join us again and look at our activities on Facebook and YouTube as well. Thank you.
Okay, we
Okay.
are on Facebook.
Okay, wonderful. Thank you. Okay, we have something from Doug Smith currently. Doug, are you ready? You have to unmute.
Okay. So one of our members, Tom Nelson, just completed and got his certificate and pin for his Astronomical League Universe Sampler Award.
Well, great. Congratulations.
He's not here tonight.
Yeah, the Universe Sampler kind of involves a whole variety of interesting things, doesn't it?
Yes, it does. It's exactly what it says. You look at a bit of everything. So,
Great.
yeah.
So, well, good. Maybe that's one that we can kind of encourage a lot of people to do, because it sounds like it's a great, kind of starter activity. Or if you haven't explored around a lot of different things, it might be an interesting program to do too.
It is one of the programs I call a starter program. It's a good way to get to know the stuff that's out there, what you can look at, what they look like through your telescope. It's a good way to, especially if you're just starting out with a new telescope, you can see what things look like.
Super. Super. Thank you so much, Doug.